Okay, in this podcast we're going to go over worksheet 5, which are the calorimetry problems, and we're going to do number 6 through number 13. Okay. So number 6 asks us about a piece of aluminum that has a mass that's provided, and it's heated up to 50 degrees. It's dropped into a swimming pool full of water at 25, and we want to know how much heat energy was transferred to the pool. So the assumption here is that what we know is that the amount of heat lost by the aluminum is going to equal the heat gained by the water. And one of the assumptions we're going to make is because the pool is going to be so much water compared to the small amount of aluminum that the pool temperature won't change from 25. So we're going to assume that we're going to end up at 25 degrees C in the pool. Okay, it might be a tiny bit different from that, but with water's enormous heat capacity, it can take a lot of heat before it's going to change temperature. Okay, so let's go ahead and take a look at what information we have. Well, as it turns out, we have enough information for the aluminum because we don't know what the mass of the water for the pool is, so we're going to determine the Q loss for the for the aluminum. So Q equals MC change in T. I know 65 hectograms is 6,500 grams. That should be 6,550 grams, but I think that's close enough. I looked up the heat capacity of aluminum on that little slip of paper I gave you today, and that's what it is. And so I'm going to drop the temperature of the aluminum from 50 down to 25. Okay, that's my change in temperature. So if I multiply all that out, I get, from a sig fig standpoint, I need 3. So I get 146,000 joules, or 146 kilojoules. Okay? So that is how much heat lost the aluminum went into the swimming pool. Alright, let's take a look at another. Alright, here we say we have 50 degrees C, and the normal body temperature is 37.2. If you drink a cup of tea with a mass of 256 grams, how much heat energy was transferred to our body? And we're given the heat capacity of water. Alright, so we're going to make two assumptions on this. The first assumption we're going to make is that the Q of the water is going to be about the same as the Q of the tea. And the other is that the body temperature is not going to change. Alright, so if you think about tea, it is essentially water with a little bit of flavorings in it. And if you think about your body temperature, if you take your temperature before and after drinking a cup of tea, your body temperature doesn't change. So there's so much water in your body, which is about 70% water, that we're going to assume that the final temperature is still 37.2 degrees. Alright, so let's look at the Q for the tea then, which is also Q for water. Okay, so I know my mass, I know my heat capacity, and if I subtract my temperature, I get a difference in temperature of 12.8 degrees. I multiply that out, and I get 13,700 joules, or 13.7 kilojoules. Alright, let's take a look at the next one. Alright, for this problem, we are looking at 5750 joules of energy are added to some granite at 24C. We want to know the final temperature of the granite, and we're given its heat capacity. Okay, so we're going to use Q equals MC change in T. We're told how much energy we have. We are trying to find the final temperature, so I think it's easiest thing to do is, rather than saying some temperature minus X, I think it's easier to say what's the change in temperature and then modify this temperature with that amount. So we're going to solve for the change in temperature. We're going to divide both sides by M times C to do so. So we're going to get change in temperature is Q over mass times C. We fill in the numbers that we have in the problem. And when we multiply it all out, we're going to get change in temperature is 16 degrees C. So that's the change in temperature. We started at 24, so we have to add that 16 to it, because if we're adding energy to the granite, we are going to raise its temperature, right? So we're going to want the temperature to go up by 16. So we're going to have a new temperature of 40 degrees C. Okay? All right, for number 10, This is the assumption we're going to make is that the Q of aluminum is equal to the Q of the water. So this is a difficult problem. There's a couple of those here. I think number 12 is also the same, where we have to figure out the final temperature for both the aluminum and the water. So this involves doing using linear equations and some algebra. So the Q for water is going to be MC change in T, and that's going to be equal to the Q of the aluminum, which is also MC change in T. So I'm setting the MC change in T for each to equal the other. Okay, so I'm going to put in what I know about water. I got 10 grams. I know its heat capacity. I know its change in temperature is going to, what I know is when I put that hot object in, the temperature of the water will go up. Okay, so when I'm figuring out the heat here, I'm going to have some number higher than 21, so it's going to be some number minus 21. Okay, when I think about the aluminum, I'm going to put in the information I have for the aluminum, 3.99 grams. I looked up the heat capacity for aluminum, which is 0.91 joules per gram C. And the change in temperature of the aluminum, it is starting at 100 degrees. If I'm putting it in water at 21, that temperature will go down. So the change in temperature there will be 100 minus X, right? Because this is going to be a smaller number when I'm done. All right, so now it's a matter of solving for X, right? So let's just take a look. So first thing we're going to do is multiply these. And when we do that, we're going to get 41.84 times X minus 21. Do the same thing on the right. Multiply 3.99 times 0.91. And now I'm going to distribute. I'm going to take the 4.184 times X and the 4.184 times 21. Okay, and when I do that, I'm going to end up with 41.84X minus 878.64. I'm going to do the same thing on the right. I'm going to distribute it, and I end up with 363 minus 3.63x. Now I want to combine like terms. So to do that, I'm going to add 3.63x there, and add 3.63 on this side for x, and that gives me this. Now I want to, now that I have x on this side and no x on this side, I'm going to add the 878.6 from this side and add it on the right side also. And when I do that, I end up with 45.47x is equal to 1241.6. Now I need to solve for x, so I'm going to divide both sides by 45.47. And when I do that, I get x is equal to 27.3 degrees Celsius. Okay, so what we have to do is assume that the heat gained by the water is equal to the heat lost by the metal. I got to think through what's happening with my temperature. My temperature of my water should go up. My temperature of my metal should go down. So I want a higher temperature here for the water. I want a lower temperature here for the metal. And then I'm solving for x. Okay. Alright, so let's take a look at number 11. And the assumption we're making here again is we have a piece of metal at 100 degrees. We drop it into water. The final temperature of the water is specified, and we want to know the heat capacity of the metal. This is just like the lab we did. Okay. And then it says to attempt to identify the metal based on its heat capacity. So earlier in the year we talked about being able to use something like density to identify a metal. So let's say we have a metal that was, let's say, found at a crime scene. We wanted to identify what it was. One test we can run is to find its heat capacity. And because all substances have different heat capacities, we can look it up on a table, and it might narrow our search for what the substance is. Alright, so Q of water is MC change in T. I know how much water I have. I know my heat capacity. I know the change in temperature. It was 23.83 minus 22, which is 1.83. So my Q of water is 76.6 joules. So if that was gained by the water, it must have been lost by the metal. So I'm going to set that equal to the mass of the metal times heat capacity times the change in temperature, which was 100 minus 23.83 is 76.17. I rearranged the equation to solve for C, and when I do that, I'm going to divide on both sides by 5.19 grams and 76.17 C, and I calculate C is going to be 0.194. Okay, so I look on that list. I didn't make a copy of it on the tablet here, but if I look at that list, there is nothing that is 0.194 joules per gram degrees C. The closest thing I find is tin, which is 0.21. Now that's off by, let's say, 10%, which for experimental work is actually pretty good. But so before I make some final confirmation about what the metal is, I will probably run another test. Either run another trial of the same heat capacity experiment, or maybe do something like run a density test, see if I can confirm that it's tin. Alright, 12 is a problem that is similar to what we had in number 10, where we're trying to find the common final temperature. We take a piece of metal and put it into some water. So again, I'm going to assume that the Q of the water is equal to the Q of the metal. For the water, I'm going to use MC change in T and set that equal to MC change in T for the cadmium. I put in what I have, what I know. For the water, I do the same thing for the cadmium. I had to look up the C for the cadmium, but it's on your little sheet. And so let's take a look at what we did with the change in temperature piece here. So if I'm dropping a piece of hot metal in, the temperature of the water is going to go up. So I have some number minus 23 here. And the temperature of the metal is going to go down, so I'm going to have 100 minus X over here. Okay. Now I've got to solve the equation, solve for X. Okay, so I'm going to multiply 25 times 4.184, and over here I'm going to multiply 37.6 times 0.23. I'm going to distribute here and here. When I do that, this is what I get. Alright, I'm going to combine like terms. Add 8.65x to both sides. When I do that, I get 11.325x minus 2406 is 865. I'm going to add 2406 to both sides. And when I do that, I get 11.325x is 3271. Solve for x, I divide both sides by 11.325, and I get x is equal to 28.9 degrees C. Alright, lastly, let's do number 13. 13 says I have a piece of metal. It was heated to 100 degrees C, plunged into water. That was cool. Temperature of the resulting mixture is 28. So the first question A is how many joules did the water absorb? So I use Q equals MC change in T. I had 100 grams. I know the heat capacity is 4.184. The change in temperature, the water went from 24 to 28. So when I multiply that out, I get 1674 joules. So B says how many joules did the metal lose? Well, it should be the same amount, right? Heat is the energy is conserved, so whatever was lost by the metal should be what was gained by the water. So it's also 1674. And then the question is, what is the specific heat of the metal? Well, in order to figure that out, I've got to do Q equals MC change in T. I know what Q is now. I know what the mass is. I can rearrange the equation to solve for change in T, or I'm sorry, to solve for C. It's going to be Q over M times change in T. I put in what I know, and I end up with this, my change in temperature, I end up with a C heat capacity of 4.64 joules per gram. Okay. Oops. And then the last question is, what is the heat capacity of a 5-gram sample? Well, if I take that 5 grams and multiply it times its specific heat capacity, my grams will cancel out here, and I end up with 23.2 joules per degree C. Alright, and that's going to do it.